Quantum mechanics is so strange and different that other fields of physics are called classical in comparison. We have to abandon the notion that objects can be described as particles with a single number position and momentum, and instead accept that objects behave like waves. Quantum mechanics handles the behavior of wave functions, waves whose magnitude corresponds to a measurement probability. That is, in one dimension, the area under the wave function squared in the little region dx tells you how likely you are to find the particle there when you measure its position. If you simultaneously measured infinitely many identical systems, the average of all the values you'd read off is called the expectation value, which can be calculated by averaging over all possible positions. Observables are any attribute of a system that can in principle be measured, like position, momentum, and energy. All observables have eigenfunctions, which represent a 100% certainty in the measured value of that observable. For example, the position eigenfunctions would be any function with a value of 1 for some position, all measurements will certainly return this position, and 0 everywhere else. The de Broglie relation connects frequency with momentum, so a momentum eigenfunction should have a perfectly definite frequency. The best defined frequency is that of a sine wave, which is the momentum eigenfunction. Notice how the eigenfunction of position is never an eigenfunction of momentum and vice versa. This is the Heisenberg uncertainty principle. It is impossible to have certainty in both observables. For some wave functions of position, calculating momentum by measuring frequency is easier said than done. Instead, we can pick out how much of each frequency sine wave is in the position space wave function, which tells us how much of each individual momentum value is in the system, giving us the momentum space wave function. Analogous to the position space wave function psi, the area under phi squared in the region dp tells us how likely a momentum value within dp is to feature when the momentum of the system is measured. In this new momentum space, the momentum eigenfunction looks like a spike of 1 at some momentum and 0 everywhere else, identical to the position eigenfunctions in position space. This beautiful symmetry goes even further. The eigenfunction with a definite position in momentum space is also the sine wave. Evidently, position and momentum are two sides of the same coin. This coin is the state of the system, a complete description of all details of the system over time, which we are only viewing from different spaces to obtain wave functions. Wave functions are simply expansions of how much of each eigenfunction or determinate value for an observable exists in the state. But it doesn't matter which eigenfunction basis you choose to represent the state in. The equation of quantum mechanics has twin versions for both position and momentum, giving equivalent solutions. This is why it is possible to transition so elegantly from space to space. They're all the same state, rephrased in new quantum languages.